Yeah, comes on everyone. Let's start off. Great. So last thing that we did was waves on a composite string. We saw reflection and transmission and stuff. The next thing, the important one, stationary waves. Others comes on. Stationary or standing waves. So first, let's see this whole thing with the pictures, and then I'll try to show this mathematically. So when two waves, so basically stationary is nothing but principle of superposition only, but the waves are a little different. So when two waves of same frequency, same amplitude, moving opposite to each other, moving towards each other. We observe certain points on the string do not move. These are called nodes. And certain points move with double the amplitude. These are called antinodes. So first, let's see this with some pictures. So let's say we got a wave here. Meaning there is more to the wave. I'm just showing a part of it. And let's say this is traveling to the right. Similarly, let there be one more wave here. Again, at this point of time, both the waves are exactly overlapping. And let this wave travel to the left. Now here, I want you to observe this point here. Let's call this point A. And just let's observe this point. What happens to this point when these two waves are moving towards each other? Now, as the red wave moves forward, this is how the wave looks. And as this blue thing goes, the blue ka wave looks like this. Right. Now, if you notice this point A, the blue is trying to push you down. The red is trying to push you up. But if you see the net displacement at A, YA will be 0. By whatever amount the red is trying to push you up, by the same amount, the blue is also trying to push you down. By principle of superposition, the net displacement will be 0. If you wait for some more time, you will get a red ka peak there. you will get blue ka peak here. That means if you see, the blue is giving you maximum amplitude in the downward direction. At the same time, the red is also giving the maximum amplitude in the upward direction. Again, you'll notice Ya is 0. So you'll observe, no matter how long you wait here, A will never move. Making sense? No matter how much time you wait and keep observing this, you will notice A never moves. Again, no equations, nothing. I'm just showing with pictures. This is what you've done in the last class, if you remember. A square and a triangle superposing what happens and all that stuff. So A never moves. Basically, this is a node. Now, same thing, if I try to see this with some other points, same thing, if you replicate with this point here, let's call it C. You will notice something similar happening here. You will notice this, the blue wave will go a little forward. This red will push this side. So you will notice here, this is being pushed down, right? And at the same time, this is being pushed up. If you see, the displacement of C is 0. Again, this is being pushed down and this is being pushed up. Again, displacement of C is 0. Again, same story. No matter how long you wait, you'll observe C will never move. And you will notice there are multiple points like this. So if that is C, let's call this thing B, right? And you will see a lot of points here. All these points will have 0 displacement. They will never move. So if you see here, A, B, C are nodes. And if you look at the distance between them, you can clearly see this is half wave. This is lambda by 2, making sense? That is half of the wavelength. So the distance between any two consecutive nodes is lambda by 2. That means on a string, if you send two waves like this, you will find at every lambda by 2, there will be a point which will not move. So distance between consecutive nodes is lambda by 2. Clear with this? Similarly, if you notice certain points, like this point here in the middle E or D, right, you will observe this is being pushed down. Let me take another picture for this. Now, if you look at this point here, D in the middle, you'll observe here, the blue is pushing it down by amplitude A. The red is also pushing it down by amplitude A. So at this point, if you see, the displacement of D will be two-way. It goes to double the displacement. And if you wait for some time, you will notice, you will get a possibility like this. The displacement of D will be 0. Meaning if you look at this point D here, this D can go from +2 to -2. And after some time, you can even get this possibility here. A is going like this. The red also becomes like this. Again, I'm not drawing full pictures here. So this is A. And this is also A. So now the displacement of YD becomes again 2A. So you will notice again, there are points like this, which is D, E, and F. These points will oscillate, the D, E, F oscillate between -2A to +A. +2A. So there are some points which will not move, and there are some points which will move with double the amplitude. So you're sending a wave of amplitude A, but you're getting double the displacement. And these points are called antinodes. And again, if you clearly observe, the distance between a node and an antinode is a lambda by 4. The distance between two antinodes is still lambda by 2. So there again, same story. So for every lambda by 2, you'll also find an antinode. Clear with this? Again, I didn't do any maths there. We just saw some pictures. So if you look at the two waves also, so this was A, this was C, this was B, this was D, this was E, this was F. This is lambda by 4 and this is lambda by 2. So here A, B, C are nodes. D, E, F are antinodes. And distance between a consecutive node and antinode is lambda by 4. Is this clear, everyone? So how does this look like?
What we have here is a frequency generator. It's connected to what's called a wave driver.
Able to hear, right?
Just a speaker.
Now, if you see here on the left-hand side, you can see that rod kind of thing. It is tied. That is a oscillator. So he connected something called a function generator. So whenever you keep a certain frequency, the rod is going to go up and down. So when the rod goes up and down, you get waves on that string, which will travel
up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back.
So now remember, in a stationary wave, what did we say? We need two waves of same amplitude, same frequency, traveling in opposite directions. So instead of using two generators, what he did, he took one source. The wave will go and hit the rod, which is a fixed end. You get an inverted wave. Now that wave will have same amplitude, same frequency, right? Opposite direction. Yeah, it is out of phase by pi. That is okay with me. Getting it? But you have same amplitude, same frequency, and opposite direction. So basically, instead of getting two waves, what we are doing, we are using the incident wave and the reflected wave as two waves. So when these two waves, the incident and the reflected superpose, we are going to see what I was telling you. You will find some points will not move and some points will oscillate with much larger amplitude.
Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive.
So if you send whatever frequency you want, it's not going to work out. You will see that later on why. But when you put certain frequencies,
I have what's called a standing wave. That is the wave that's sent down.
can you see that picture, how it looks? Can you see that bulge? Can you see that white spot in the middle where his finger is? That point is not moving. No matter how long you will wait, you'll observe that point will never move. And you can see the bulge in the middle. That thing is actually moving much, larger amplitudes.
Constructively interferes with the next wave that comes down right at this point. Now the waves that reflect deep
If he catches in the center, still nothing is going to happen.
I can touch it and it's still
Because that's a node, right? It doesn't move anyway.
So the node is not moving. Here it's moving up and down, and here it's moving up and down.
No.
And we'll see that in a second with the high-speed camera.
If you see in the slow motion, actually this is how the string is going. Can you see the picture? The thing is, this thing is going so fast. If you put a frequency of, let's say, 50 hertz, this is oscillating 50 times up and down. You start thinking it looks like a loop. You're getting it? That blur kind of shape which you're seeing. When I was 11th, I used to think the string became two pieces. I never understood how can string break into two pieces and come back again. So the thing is, it is going so fast, it gives you an illusion that, it forms like a loop. It looks stationary. That's where the name comes, stationary wave or a standing wave. So the whole thing looks stationary. This is in slow motion. See how it goes. It is actually going this way. Now, if you see normally, this is how it looks.
What's called the second harmonic. It's the second.
Can you see that picture? How it looks? It looks like a two strings, isn't it? It's basically an illusion. It is going so fast, you think it looks like a loop, whereas actually that is only one string.
Second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, this is a node, and the middle. So we have three nodes this way. Now, like I said,
now if you change frequencies, now we can understand. What did we just prove right now with the pictures? The distance between two nodes is lambda by 2. Agreed? So if you increase the frequency, the wavelength will decrease. If wavelength decreases, the distance between the nodes will decrease. That means you can put more loops in the same length of the string. Is that making sense? If you bring the nodes closer, that means the length of the loop is becoming smaller. You can put more loops on the same length of the string.
And there we go.
So here he decreased the frequency. So that this is a first harmonic. We will talk about that. It is one loop. Slow motion. Look at how it looks in normally.
It looks scenario.
There it looks like a loop.
Now I can find multiple times.
You increase the frequency, you get two loops. Three loops actually.
So that's the third harmonic. How many wavelengths is this? Well,
you can clearly see that is one loop and a half.
And a half. One and one half wavelengths.
Yeah, that is each loop is lambda by 2.
It's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is one and one half wavelengths.
There. Now, one more thing I want you to observe here. Look at that first loop and the second loop. When the first loop is going down, second loop is going up. They always go opposite to each other. See. Now see, first loop is going up, second loop is coming down. So you'll observe the two loops are always out of phase by 180 degrees. When one is going up, the second loop goes down. So 1 and 3 will be in sync, 1 and 2 will be out of phase. So all odd number loops will go together up, all even loops will come down at the same time. They're out of sync by 180 degrees.
So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic.
You keep increasing the frequency, then you can get 6 loops.
Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have.
So that's how it goes. Clear with that? So that whatever I was showing you with the picture, that is what it looks like. So on a string, if certain points are not moving and certain points are moving double the amplitude, the whole thing looks like it forms loops. So whenever they have to represent a stationary wave in books and all, this is how I will write a stationary wave. So we represent stationary waves with this symbol. So we show it like a loop. I'm not drawing it properly. Like this. So what is this exactly? So I used to get confused, like, yeah, why are you getting two strings? So these are actually different positions of the strings. So if I actually have to plot, so let's say this is the string ka position at T1 and T1. Next moment, this is how the string will look, T2 and T2. Next moment, the string will become flat. Now in the entire process, the midpoint is not moving. This is T3 and this is T3. Next moment, this is T4 and T4. That is your T5 and T5. Is this making sense? So these are actually different positions of the string at different times. Now this happens so fast that one string is just going up and down so fast, it looks like a blur. So it gives you a feeling as if there is a loop. Clear with this? So just imagine if you say frequency of 50 hertz, it's going 50 times per second. We humans can't see anything more than 20 times per second. We think it's a video. Must have played with that flip book, na? It kind of looks like that. Clear with this, everyone. So there, everything that I showed you is pure pictures with principle of superposition. Let's try to do this mathematically. Now, mathematics will make more sense because the general proof is in max, but I never felt it like, it feels like, right, but it never feels convincing. Like, you'll always feel like we just, set up the answer. Sometimes happens, you see the question, you know the answer, you try to make it up. Something of that sort. So, equation of the stationary wave. For now, we will just write a normal one. Later on, I'll teach you a more general waveform. So let's say y1 is equal to a sine kx minus omega t. Remember, you need two waves of same amplitude, same frequency. Only thing, they should go opposite to each other. So it's kx plus omega t. So y resultant will be y1 plus y2. To a sine kx cos omega t. Sine a plus sine b. Now, if you look at this equation, it doesn't look like our general wave equation. That is because our general wave equation is for a progressive wave. This is not a progressive wave. This is a combination of two progressive waves. So be careful. Now, in this wave, if you see, there are two terms here. This 2a sine kx, this represents the amplitude. End of the day, no matter what wave and all you talk about, it is always about an SHM for us. This is an amplitude of a particle at a coordinate x. And this cos omega t represents SHM of a particle. So basically, a stationary wave is nothing but infinite particles oscillating in SHM with different amplitudes. What is a progressive wave? Infinite particles oscillating in SHM with same amplitude. Meaning, if you have to just, break it down into the simplest form, that is what I'll call. The regular wave we study is an SHM of infinite particles. All have same amplitude, but all are out of phase. Everyone has a different phase angle. You are going to extreme at some other time. I go to extreme at some other time. A stationary wave is all particles in SHM, right? And all have different amplitudes. And particles are in phase in a loop. So we will see that. This represents SHM of a particle. at x. There. For now, this is our equation. There is a more general equation we'll see later on. So that means when you take the wave, this is x is equal to lambda by 2. This is x is equal to 0. You will observe different particles have different amplitude. This is 2a sine kx. So at a distance x from here, this particle has an amplitude 2a sine kx. And there you can see this thing, different particle. That means the particle at x will never exceed 2a sine kx. This will go to maximum 2a. This will occur at a distance of lambda by 4. That's your antinode. These are your nodes. They will never move. And if you observe, all are in phase. Means all this will go to their maximums at the same time. All will come to their minimums at the same time. Progressive way में ऐसा नहीं था. Progressive way में everyone is going to their maximums at different times. But all go to their same height of maximus. The level is same. Are you getting the key difference? Let's see first what is common between them. Progressive wave, stationary wave. First thing that is common, all are executing SHM. That is a common thing. First difference. We will write this later on. Progressive wave में all go to same height. Stationary में all don't go to same height. Second difference. Progressive wave में all have different phase differences. 0 to 2 pi. Everyone is going to their maximums at different times. In a stationary wave, in one loop, all go to maximum at the same time, all come down at the same time. So primarily, the major two differences are amplitudes and phase angles. The thing which is common, they're still executing SHMs. Meaning, fundamentally, if you think about it, that's the difference between them. But again, in the end, we will write those differences later on. So if you see different particles have different amplitudes. Clear with this, everyone? Clear with this? Any doubt so far? Next thing. Now we have taken this amplitude to be to a sine kx. So for nodes, amplitude is 0. They'll never move. That means sine kx is 0. That means kx will be equal to n pi. K is 2 pi by lambda, x is equal to n pi. We get x is equal to n lambda by 2. That means if you put n0, 1, 2, 3, everything, you will get x0, lambda by 2, lambda, 3 lambda by 2, so on. These are the nodes. And you can clearly see distance between two nodes is lambda by 2. Isn't this what we proved with pictures? We proved the same thing mathematically. So for every distance of lambda by 2, you will find a node. For antinodes, the amplitude is 2a maximum. Sine kx is equal to 1, and we will get kx is equal to 2n plus 1 pi by 2. Magnitude actually. So I can write this thing as kx is equal to n pi plus minus 1 power n pi by 2. This thing is simply odd numbers of lambda by 2. Lambda by 4. So here we get positions as lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on. These are exactly between the nodes. And you can see the distance between them is also lambda by 2. Distance between node and antinode is lambda by 4. Okay with this? Next thing. Great. So we got the equation part. So when we study this, so the instrument we use to study the stationary waves is a sonometer. If you had been to the lab, you must have heard this term at least. So, and not only this thing, I will in some time you're going to see this. You have used, you have used this sonometer. I'm pretty sure in your life you must have touched at least once. And I'm pretty sure you used it. This is pretty common thing. We'll see the practical applications of it. A sonometer, if you go to a lab, you will find something like this. Again, this is a simplistic diagram from the textbook. In the actual sonometer lab experiment, you have multiple strings. So few things here. So this is your adjustable mass. So by changing the mass, you can change the tension. And if you can change the tension, you can change the wave speed, which is root over T by mu. Here we have two wedges. By moving these wedges, we can change the length of the string. Now for simplicity, we will draw the picture like this. X is equal to 0, X is equal to L, and we have a tuning for frequency F. That is how the picture will show for a sonometer. So how do we use this? First of all, so this is the same video that I showed you now, isn't it? It kind of looked like this only. One side you have an oscillator and one side is this. So what is the first possibility? Now when you have drawn this sonometer, so this is your x0, this is x is equal to L. Now tell me one thing, these points on the edges, right, they're fixed. They cannot move. So in a stationary wave, which points cannot move? Nodes. Therefore, x is equal to 0 and x is equal to L must be nodes. Because they're fixed points. So basically, you have created a physical constraint. You're telling the equations, boss, you generate whatever frequency you want, you can get whatever stationary you want, but remember, you have to make sure 0 and L are nodes. As long as you satisfy this condition, you can get any stationary waves. So in the first possibility, now you tell me, if this point and this point should be nodes, what are the first possibility? One single loop. Remember, I have no other constraints. My only constraint is those two should be nodes. So 0 and L. What is the distance between them? Lambda by 2. So lambda by 2 is equal to L. So wavelength will be 2L. Then we know frequency is equal to V by lambda, which is V by 2L. This is called as fundamental frequency. So fundamental frequency is simply the minimum frequency for stationary wave to form. You cannot get any wave, stationary wave below this frequency. This is also called as first harmonic. We will talk about that in the next page. This is your first possibility. What is the second possibility? Again, remember, the only condition I have is make sure the two things on the edges are not moving. That means I can have two loops, isn't it? I don't care whether something in the middle is moving or not moving. As long as I satisfy that x is equal to 0 and L are nodes, everything else is okay with me. This time, this is lambda by 2. So 2 times lambda by 2 is equal to L. Frequency will be V by lambda, which is 2V by 2L, which is 2F1. So this is called as second harmonic or first overtone. So what are these harmonics? So harmonics are integral multiples of fundamental frequency. So if you take an integral multiples of the fundamental frequency, whatever frequency you got f, uska 2f, 3f, 4f, all these are called harmonics. So this is called first harmonic because it is one multiple of fundamental. This is two multiple. Integral multiples of fundamental frequency. What are overtones? So over the tones. These are the frequencies after fundamental frequency. So this is the second harmonic is the first frequency after the fundamental. So it's the first overtone. What is the third possibility? 3 loops. So here we will get 3 times lambda by 2 is equal to L. We get F3 will be 3V by 2L, which is 3F1. Third harmonic and second overtone. Clear with this? So from here we can see we are getting one generalized formula now. Clear with this? Now if you write a generalized formula, so the frequency for an nth harmonic will be n by nv by 2L. This can be written as n by 2L. V is nothing but root over T by mu, wave speed. This is a general formula for a sonometer. Fn is the frequency for the nth harmonic. In this case, it is also n loops. V is the wave speed. T is tension, mu is your linear density. L is the length of the string. N is the number of harmonics. So where did you see this before? If anyone here has learned how to play an instrument, a guitar, a violin, any stringed instrument that you have seen, actually every musical instrument is based on stationary waves. Fundamentally, every stringed instrument is a sonometer. So if you take a guitar, it's a sonometer. a violin is a sonometer. Your piano is actually also sonometer. In a piano, you have strings and where hammers hit them. So how does this work? So anyone is planning to learn a musical instrument, or you're already a musical instrument? This will help you to actually understand, because see, the instructor there will simply tell you, plug the string here, catch this thing like this and all. But fundamentally, even you might not have an idea like why is this working in the first place. Look at this formula. So this formula tells you how to generate different frequencies. So reverse, right? If I give a frequency, you'll oscillate. If I make you the string oscillate, I'll get that frequency back. Now in a guitar, if you see, first thing, look at the strings here. Can you see the thickness of the strings? If you take a guitar, you have 6 strings. All have different thickness. Means what? You have different Muca values. Meaning at the same length, if I plug the 6 strings, I get 6 different frequencies, no? So you're changing Muca value. So different thicknesses have different mu values. And the instructor tells you, right, put the hand here and plug the string. And also if you change your position of your finger or hand, whatever, you're changing the length of the string. Did you ever hear this thing? I'm tuning the guitar, I'm tuning the instrument. What do you mean by tuning the guitar? For example, let's say if you catch the point here and if you plug the string, you should get a sa, let's say. So normally that's how you check. When you're plucking there, you should get sa, 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 but you're not getting sa, you're getting something more weird. Then what you do, the screws which are there, you tighten the screws. You're changing the tension. So you keep tightening the string till you get that sa at that particular point. Then you know, okay, this thing is set there. So tightening the screws will adjust the tension. So what are the harmonics then? Now these things are also called as octaves. So when you say this thing, you know the thing. So sa, re, ga, ma, pa, da, ni. Sa comes again. Observe kiya kabhi? So sa keeps coming back again. So what is this sa then? This is your first harmonic sa. I don't know the numbers exactly, but I think it is 100 hertz. The second sa, if you keep increasing the frequency, you'll get a 200 hertz. Again, you will hear a sa, but this is more sharper. So if anyone has learned instrument, right, you must have said, right? Okay, play sa, but at a higher frequency, higher note, they say. Play the same thing at a higher note. Matlab, he's saying, go to the next harmonic. So the second sa, you will, when you hear it, it is a sa, but you'll find it more sharp. Right? It's like sa, more, it is more, I don't know what to call it. I'm not a music person, but you're getting it. One is more sharp. As the frequency keeps going up, right, your ears will start ringing. You must have observed when a high frequency it starts pitching. So this is a second harmonic sa. This is around 200 hertz. If you keep going higher, again you will hear a sa. This is the third harmonic, and so on. So these are your harmonics. So next time you're playing an instrument, you know this thing, why you're catching the string at a particular position, why this string and not that string, what is tuning an instrument, what are these octaves? What do you mean by, play the same thing at a higher note? When you say higher note, he's telling you to go to the next level of frequencies. Clear with this? Theoretically, that's what it means. But it has a lot of practical applications. So your entire musical instruments are based on this. Play with this. So currently we'll be playing with that one formula there and the basic, whatever I taught you, node, anti-node, the distance between them and all that stuff. And the equation. So for now, we will use this equation. 2a sine kx cos omega t. You can copy down in case you don't remember. we will need that and this equation, nb by 12 or n by L root t by mu. That equation is not actually the general equation, but for now, let's take it one step at a time. Let's not dump everything together. All clear with this? Any doubts on the theory so far? Stationary wave. So that is the main idea there. The same thing is there in sound waves also. The theory will look similar, but this time we'll talk about sound waves. So let's see a few questions. Let's get used to this and then we'll slowly bump it up. We got a block here. This is rho b. We have a liquid here. Density is rho L. We have a tuning fork here, frequency F. This is x is equal to 0, x is equal to L. String oscillates in second overtone before immersing in liquid. And third overtone after immersing in liquid. Find rho b by rho L. Block का density rho b, liquid का density rho L. Everything else is same. The tuning fork frequency, everything else is same. There. Straightforward question. I just messed up the tension there. Right, Purvaja. Let's see. So in the first case, tension T1, this will be rho b volume G. Second case, T2, this will be rho b Vg. The bind force will be rho L Vg. Now, be careful. The words are second overtone and third overtone. Second overtone meaning third harmonic, third overtone meaning fourth harmonic. So here, if you see f is equal to n by 2L root over t by mu, here everything is constant. F is constant, L is constant, mu is constant, n into root t is constant. So n and t are getting messed up. This n is your harmonics. So second overtone is 3 root over rho b Vg. Third overtone is 4 root over rho b minus rho L Vg. So solve this, you will end up with 9 rho b, 16 rho b minus rho L. You will get rho b by rho L is equal to 16 by 7. Hmm. Clear? Any doubts on this? So straightforward equation. You're just playing around with that. Let's see one more. Y is equal to 10 sine pi x by 3 cos pi by 6t. Remember our general equation so far what you have given, y is equal to 2a sine kx cos omega t. Here x and y are in centimeters. Find velocity and acceleration of the particle. That x is equal to 2 centimeters and t is equal to 2 seconds. Find v wave. Max speed and acceleration of a particle. If length of the string is 30 centimeters, find the number of harmonics or find the number of loops. Find phase difference between x is equal to 2 centimeters, x is equal to 2.5 centimeters, x is equal to 2 centimeters, and x is equal to 3.5 centimeters. Yeah, let's get the total 5 equations. Let's get them all. Mhm. See. How to do the first one? Simple thing, kinematics. How do you find velocity and acceleration? Differentiate. Where you get struggling so much. You want velocity, dou y by dou t. You want acceleration, dou square y by dou t square. Partial differentiation. So y is equal to 10 sine pi by 3x cos pi by 60. Velocity is dou, remember velocity of the particle, dou y by dou t. That will be 10 pi by 6 minus sine pi by 3x. This will become sine pi by 60. Axis of the particle, dou y by dou t minus 10 pi square by 6 square sine pi by 3x. This will again become cos pi by 60. There. You can substitute x is equal to t and everything and finish it off. What is omega? Pi by 3. Pi by 6. What is k? Pi by 3. What is v wave? Omega by k. Your progress formulas are still valid. What is Vp max? Do you remember from SHM what is Vp max? A omega. So here it is 2a into omega because 2a is our maximum amplitude. So in this case, it is 10 basically. This is your 10 basically. So be careful. I'm using 2a. In some books, they will simply say a is the net amplitude. You're getting it? So 2a, in this a is the amplitude of the individual waves, initial waves. Are you getting it? But in some books, they will say they'll directly write y is equal to a sine kx cos omega t. And they'll say a is the amplitude of the antinode. Are you clear with this? So I'm writing the amplitude in terms of the individual waves. So A is the amplitude of the two parent waves you can call, which we have used. So 2A is the amplitude of the antinode. But sometimes in some books and some questions, they will give you amplitude of the antinode directly. So don't get confused. So what is AP max? Romer assessment ka formula, A omega square. So 2A omega square. Everything works because it is still an SHM. What is the third question? Length of the string is L, find the harmonics. K is 2 pi by lambda is equal to pi by 3. So lambda is equal to 6 centimeters. So length of one loop is 3 centimeters. And the length of the string is 30 centimeters. Therefore, number of loops are 10. Is a 10th harmonic. Clear with this? What about D? Think about that. I'll give you a minute. Find the phase difference between 2 and 2.5 and 3, 2 and 3.5. Now here, be careful in the D part. Phi is equal to 2 pi by lambda into delta x. This is wrong. This we derived only for progressive waves. You cannot use this for stationary waves. That's because when you look at a stationary wave, how they move, look at this. All these blue ones are going up. All right, and let me take the red ones. So if you see, all these particles in the first loop are going up. Here, all these red ones are going down. And here, this is going up. Remember, this is the positions of the string. I hope you're getting it. These are the different positions of the string at different times. So meaning, if I remove the blue one, I think that will make more clear. This is how the string would be, isn't it? When they're oscillating, this is how the string will be at some time. Later on, it will become blue color. That means all these points will come down. All these points in the second will go up. All these points in the third will come down, and so on. So few points here. So all points in a loop will go together and will come down together up. So they'll have a phase difference of 0. All points in a loop and alternate loops are in phase. So phase difference is 0. All points in consecutive loops are out of phase. That's it. There are only two answers here. Unlike a progressive wave where you can have an answer anything from 0 to 2 pi, either you get 0 or you get pi. That's it. There are only two answers. So points in consecutive loops are out of phase by pi. So that is one major difference. So that formula you derived it from progressive wave. You can't use it here. Now look at our points here. Which points you want? 2 and 2.5 and 3.5. So this is x is equal to 0. We proved one length ka loop is x is equal to 3. So x is equal to 2.5 will be somewhere here and x is equal to 3.5 will be somewhere here. And this is how you have to check. So therefore, phase between x is equal to 2 and 2.5, they're in the same loop. Phase is 0. X is equal to 2 and x is equal to 3.5, they're in the opposite loops. Phase is pi. This is one major mistake people do. So be careful with that. You cannot use that formula here. This is not a progressive wave. And if you remember the derivation for that 2 pi by lambda delta x is also something else. You replaced x with x plus delta x, and then we said k delta x must be 2 pi and all that we did. You can't do that in a progressive space stationary wave. Any doubts on this? Take a break. Come back by 9:41. Any doubts so far?
They're on page 75.
Chalo, come back in 5 minutes. That same thing. And they'll give you like this: find phase difference between x is equal to 3 centimeters and x is equal to 7 centimeters. So if you mix up and use the formulas, you will be gone. So this is a progressive wave, kx minus omega t. Stationary wave is a combination of two progressive waves. So the formula doesn't look like that. You can't use the phase difference thing. The reason you couldn't use that v wave is omega by k and all that is because this omega and k will belong to the parent waves, isn't it? Whose omega and k didn't change. So it works out. Get this thing. This will be a pretty good mains level question. Most people, they'll ask for stationary waves, they'll write the answer for progressive wave and come. Unfortunately, that answer will be there. Just give it a try. Let's see. So for the first one, we can use phi is equal to actually we can directly use k delta x, which is only 2 by lambda delta x. So this is pi by 3 and 7 minus 3. 4 pi by 3. But with this guy, you have to be careful. K is pi by 3 to pi by lambda. Lambda is 6 centimeters. That means the loops which you get, x is equal to 0, x is equal to 3, x is equal to 6. This is x is equal to 9. X is equal to 3 is actually a node. That would be a problem. Because node के लिए ना phase is not defined. It's not moving only ना. So let me just change this. X is equal to 2 and x is equal to 7 centimeters. This is 7 minus 2. This will be 5 pi by 3. So here x is equal to 2 is here and x is equal to 7 is here. So this will have phase 0. This will have pi. This will have 0. So the answer is 0. Clear with this? There, this is one thing. Be a little careful with that. Next one. Next one. a string of length 120 centimeters. Oscillates in fourth harmonic. Maximum amplitude is 4 mm. Find the minimum distance between 2 points with amplitude 2 mm. So there will be multiple points with amplitude 2 mm. So between them, what is the minimum distance between them? Ten, 10, okay. Let's see if you draw the picture here, 120 centimeter. So we have 4 loops. X is equal to 0, X is equal to 30 centimeters. We know the amplitude is 2a sine kx. This is 4 mm. So this is 2 mm is equal to 4 mm sine kx. So kx will be, again, it can be pi by 6, it can be 5 pi by 6, and so on, multiple things, right? If I take the simplest one, pi by 6, then that would be, that is 2 pi by lambda, we get lambda by 12. And here lambda by 2 is 30 centimeters, lambda is 60 centimeters. So we get this is 5 centimeters. So let's understand the meaning of this. So from this point, if I go here, this guy will have 2 mm. Similarly, from this edges, symmetry, this will be 2 mm. So from here also there will be 2 mm. So one of the most common mistake, you know what? So here this distance is 20 centimeters, isn't it? This distance will be 10 centimeters. So that actually the distance is alternating 10, 20, 10, 20, 10, 20. And the question asked is minimum. So you should take 10. Are you clear with this? I never told you, in the same loop. If I had said to this, find the distance between the 2 points with 2 mm in the same loop, then you should have taken 20 centimeters. But the question was not that. So So what you got this pi by 6 is from the 0. That is the first position where you get this 2 mm ka thing. So the answer is 10 centimeters. So be careful, 10, 20 both will be there. Make sense? So if the question was within the loop, it would have been 20. So the minimum distance is actually between the alternate loops. Any doubts on this? Let's see more questions. Okay, let's get them. Be careful, they said same metal. Matlab rho is same, not mu. Right, Saish. Yeah, it looks like most of you got it. Let's see. First one. A wire of length L having tension T, radius R vibrates with fundamental frequency of another wire, blah, blah, blah. Fundamental frequency matlab N is equal to 1. So first thing, rho is equal to mass by area length. So this is mu by area. So mu is equal to rho into area, which is pi r square. So your formula F is equal to fundamental frequency. So 1 by 12 root over T by mu. So this is proportional to 1 by L root tension by R square. So this is root T by LR. This is the ratio we are looking at. So this is f by f dash root t by lr, and this guy is root 2t this is 12 2r by root 2t. That's 2 root 2. C option. What about C? A string of length 1.5 is with 2 ends clamped and vibrating. This we just now did it. 2 points having 2, but he said fundamental node, na? So you should, so that is a big one. This is 4 mm. This is 2 mm. So we get 2 mm is equal to 4 mm sine kx. Kx is equal to pi by x, and x will be so here lambda by 2 is 1.5 meters. So lambda is 3. That's 2 pi by lambda. One by 4. Remember what you got was this. This was 25 centimeters. Similarly, there is one more here. Symmetry, it should be 25 centimeters from there. So he's asking between these two, this is 1 meter. The option. Be careful, this and the previous one are different. There's only one loop here, fundamental node. There is no second loop. Clear with this? Let's see a few more. Any doubts on this? Great. Next one. Hmm. Yeah, resonant frequencies means harmonics only. Resonant frequencies, no, matlab, these are the frequencies for which you get that thing. It's called resonance. Let's see. 21 AM, let's see. A 75 meter string fixed at both ends produces resonant frequency 384 288 without being any other resonant frequencies. That means there's nothing in the middle. So if this is n, that must be n plus 1. That is one way, but you can actually guess also. The difference must be one harmonic, isn't it? The difference between two frequencies must be one harmonic. But so, ठीक है, but फिर भी we will do it. So this thing, so 384 must be n plus 1 v by 12. 288 must be nv by 12. Now we can even find n also. If you subtract them, how much is that? 96. 96 is equal to v by 12. So from here we get v is equal to 2 into, that's 3 by 4 into 96. 2's a 48, 144 meters per second. Now, much faster would be, you can argue the difference between two frequencies must be one harmonic. And then you're done. What about 22? Keep going. Okay, Ishana, I got something. Would be right, Ishana. Right, Saish. Let's see. A string of length is fixed at both ends. It is vibrating in third overtone, matlab fourth harmonic. There are 4 loops. With the maximum amplitude is A. So here 2A is 2 capital A small a. The amplitude at a distance L from one end is T. Yeah. So 4 loops, right? 4 lambda by 2 is equal to L. Lambda is equal to L by 2. So K will be 2 pi by lambda, which is 4 pi by L. And we know amplitude is equal to 2A sine kx. Here 2A is small a. Sine kx 4 pi by Lx. And now you're telling me you want an amplitude at a distance of L by 3. So that would be A sine 4 pi L by 3 by L. That's 4 pi by 3. It'll end up to be root 3A by 2. Cord is attached to 6 loops. Tension is 36 newtons. Meaning is we are assuming the frequency is same. N by 12 root T by mu. So here basically N into root T is constant. So that is 6 into root 36 is equal to 4 into T. How much is this? 81. Clear with this. All these are proper mains level questions, right? Yeah, I think most of you did get it. Clear with this? Next thing. So sonometer wire has length 114 centimeters between two fixed ends. There are two bridges which are placed to divide the wire in three segments. 1:3 to 4:7. Meaning when you keep these two things, this is one string here. I'm marking in red. Then I'm marking one in green. So this becomes the second string. I'm marking in sky blue. That becomes the third string. So there you created three strings in the ratio 1:3 to 4. Then he's asking what is the, no, he is asking the fundamental frequency is 1:3 to 4. Then he's asking where should the bridges be placed. So just to give an idea, if this is the picture here, this is x is equal to 0. So I want the position of this first bridge B1. I want the position of second bridge B2. This string is anyway x is equal to L or 114 centimeters. The position of the bridges. Let's see. 72, 171 by nah. Aditya, that looks right. Ishana, I think somewhere good enough. Let's see. First of all, again, we are talking about all fundamental frequencies. So this is 1 by 2L root T by mu. Everything is constant. So 1 by L. So L1 is to L2 is to L3 will be in the ratio of 1:1 is to 1 by 3 is to, it's the reverse ratio of frequencies, 1 by F1, 1 by F2, 1 by F3. So he gave these ratios in 1:1, 1 by 3, and 1 by 4. There. So if you just multiply with 12 everywhere, I'll get 12:4:3. So for the first length, it will be 12 by 19 into 114. That comes to around 72 centimeters. So the first bridge is placed at 72 centimeters. Be careful, this L1 is the length of the string. So this was L1. So when you get L2, that is not the answer. It should add 72 to it. So L2 will be 4 by 19 into 114. This thing is around 24 centimeters. So this was L2. So 74 plus 22, the bridge is at 96 centimeters. Making sense? So the question is, where did you keep the bridges? He didn't ask you the length of the strings. So 72 and 96. Easy? Let's see one more. Let's say we have a composite string. This is fixed here. This is 9 mu. Let's say length is L, this is 4 mu, length is L. This is the interface. Find the frequency for second harmonic. I can mess up the lengths also, but okay. Find the frequency for the second harmonic. Let's see. So first thing, what is the catch? In this thing, you need to understand there's a problem that we have. If this interface, every time this interface moves up and down, what will happen? You'll get a transmitted wave and a reflected wave, isn't it? And that's going to mess up the whole thing, isn't it? So you'll start getting waves into, AR, AT, and that's the problem. So the interface is a problem. So what is the catch in this? You have to make sure the interface does not move. So on a composite string, if you want to generate a stationary wave, you have to make sure that interface is a node. Because every time that interface moves, you'll get transmitted and reflected waves. The whole thing is going to get messed up. Clear with this? That's it. That is the only catch in this problem. So you will argue this is a node, and then this becomes one string, and this becomes one string, isn't it? You can do the formula for two different strings. So that's your thing there. So for stationary waves on a composite string, the interface has to be a node. Or else you cannot generate stationary waves. Because if interface moves, it will generate transmitted and reflected pulses. And they just won't stop with that. Those pulses will hit this wall and come back again. Again, interface will move. You're getting it? This will never stop. The whole thing gets a messed up thing. So then that's it. Once you got that idea, it is pretty straightforward. You can treat both of them as two different strings. Remember, they'll have the same frequency. N1 by 12 root over tension is also same. Mu1 is equal to N2 by 12. Let's just write this up. 4 mu root over T by 9 mu. We get N1 by N2 is 3 is to 2. So 2 is to 3. So what is the meaning of this? The meaning of this is whenever you get stationary waves, the loop should be always in the ratio of 2 is to 3 loops. You cannot generate whatever amount of loops you want. Now there's a restriction. So the first harmonic of this system so if you keep sending different frequencies, the first time you will see a sustained interference, or this thing, what you call that. A proper stationary wave is when this guy has 2 loops and this guy has 3 loops. That means N2 is the third harmonic, and for this guy, it is the second harmonic. You getting it? So second harmonic of the left string and third harmonic of the 9 mu string is the first harmonic of the composite string. Is that making sense? So again, understand the meaning of first harmonic, the minimum frequency for a stationary wave to form. So the minimum frequency is when N1 is 2 and N2 is 3. So the second harmonic of the 4 mu string is the first harmonic for the composite string. Your first harmonic is 1 by L root over T by 4 mu. What is the second harmonic? Remember, the ratio has to be 2 is to 3. Meaning this guy will form 4 loops. This guy will form 6 loops. So N2 is equal to 6 and N2 is equal to 4. Your second harmonic will be 4 by 12 root over T by 4 mu. Clear with this? That's how you handle composite strings. I could have kept one more string here. The story is still the same. Every interface has to be a node. Suppose, let's say, after solving, you got N1 by N2 is equal to root 2. What is the meaning of this? This is an irrational number, right? You can never get an integer. So that means you can never form a standing wave on that. It should be always in the form of P by Q, where P and Q are integers. Got this? If you got an irrational number, N1 by N2 is root 2 or root 3, you're done. There is no integers which will satisfy this root 2. That means on that system, you cannot create a stationary wave no matter what you do. Is that clear with that? If N1 by N2 is, let's say, at root 2, then this implies stationary waves cannot form. Yeah. Let's see one more. What if on the right hand side, instead of a fixed end, we have a free end? X is equal to 0 and X is equal to L. Everything is same. I just removed the free end. Find the frequencies for stationary waves. Think about it. The fixed end is what? A node, because it can never move. What about a free end? Think about it. Let's say if a wave is coming, okay, to a free end. When half of the wave gets reflected, how will the picture look like? This will be like this, and the reflected will be like this, isn't it? So what will be the amplitude then? Two-way, na? You're just folding the wave onto itself, isn't it? Now you tell me, in a stationary wave, which point has double the amplitude? Antinode. That's it. So the free end must be an antinode. A fixed ends are always nodes, free ends are always antinodes. Now try to get them. Then, you know, first possibility, second possibility, and so on. Hmm. Hmm. Right, Vihan. What is the first possibility? It's like this. Again, remember what is the meaning of this? These are different possibilities of the string. So when the ring is here, this is your T1. After some time, the ring will come here. This is your T2. Then the ring becomes straight. This is your T3. This is your T4. This is your T5. So that is how it is going. Left side is fixed and the right side is oscillating. So that is how we draw this thing. So this thing is lambda by 4, the distance between node and antinode. The lambda by 4 must be equal to L. So frequency will be V by 4L. This is your first harmonic and fundamental frequency. What is the second possibility? Remember, left side must be a node, right side must be an antinode. That is the only condition you have. You have to get a full loop and you have to get an half loop, isn't it? There is no other way. You can't get a thing like this. This is not possible. So you have to get 1.5 loops. So this is lambda by 2 and this is lambda by 4. So 3 lambda by 4 is equal to L. So lambda is 4L by 3. So you will get F3 will be 3V by 4L, which is 3F1. So you'll notice something. This is your third harmonic. Second harmonic is missing. And this is your first overtone. This is where you start getting problems. So be careful. Every time first overtone is not second harmonic. Overtone का definition is the frequencies after fundamental are called overtones. You're getting it? I don't care whether that is second or third or fourth. The frequency after fundamental is the first overtone. In this scenario, there is no second harmonic. Now, if I go for the next one, third possibility, we will get two loops and an half loop. So the harmonics will be always differing by wavelength of lambda by 2. So this would be how much? Lambda by 2, lambda by 2, and lambda by 4. 5 lambda by 4 is equal to, well, you can clearly see this will be F5, which will be 5 V by 4L. This is 5 F1. This is the fifth harmonic and the second overtone. This is the reason why when you make stringed instruments, you will never make a stringed instrument with one side on a free end or something, because you will miss half the frequencies. So by chance, let's say someone makes a hypothetical instrument with a free end and one side is fixed and both the sides fixed. This fixed ends will generate double the frequencies than the other one. The sound will be more rich. So the frequencies for this thing Fn will be 2n plus 1 B by 4L. Here n ka numbers can go from 0, 1, 2, 3. I won't call n is harmonics. N is overtones. So there is no zero overtone. So first overtone, second overtone, and so on. So here even harmonics are missing. Interestingly, if you keep free ends on both the sides, then how do you think it looks? No, we can't do that, but if we create it, we'll see this in sound waves. Then your first harmonic will be like this, na? Which is actually still a full wave. This will be as good as both the sides fixed. It won't make a difference. Clear with this? So this is a non-standard one. This is not a sonometer, but it is a variation of the sonometer thing. Clear with this? There, that's a bit about the stationary waves and everything. Like you said, so today we did all most basic ones and everything. So next class when we catch up, we will do energy in a stationary wave. We will see the general equation of a stationary wave. We will see a few more questions. And then we will start off with the sound waves introduction. So, okay, with that we'll wrap up for the day. Hope everyone has finished your AC sheets. Right, and do finish off EMI and AC is important, right? If you have not done, do try to finish off this Friday, and after Friday you have to start doing waves. If you're doing HCV, waves has two different chapters: waves on a string and sound waves. So I think even sound waves, after this sound waves will be quite faster. If you understood what we did today, the rest of the chapter is quite manageable. We have Doppler effect. It's removed from the mains portion, but advanced mein hai, so we will still do it.